Okay, good morning. This one I'm actually going to keep kind of short and sweet because we did a lot of work earlier in the week, and I think it makes sense to keep this one a little bit more brief. And then where we're moving to next is I'm going to talk about mirrors. It's going to be our last topic. I'll do it in one lesson, and then we'll talk about what it looks like to wrap up the unit and going into the next one. So Monday for sure is another lesson of new material, and then I will give you some information once that lesson's done about how we're going to wrap up the unit. So the last topic was reflection versus refraction. And then if you went all the way to the end, you learned how to use Snell's law, which allows you to mathematically calculate n values for materials based on observations of light rays or what the angle of refraction would be as you shoot a light ray into a new material. So here is the last piece to sort of add on to that. I'm going to show you a picture under the document camera here. It's this image right here, which is the one I want to point out to you. So you have, in this case, a light ray that's coming from this source right here, and it is heading from the glass into air. So the light is actually coming from inside the glass and heading to the air. So the angle determines what happens next. If it comes straight on like this, it just keeps going. Okay, so that would explain why if you held a straw upright, you're not going to see that difference between the air and the water medium. As you change the angle here, you change the angle of refraction. What is consistent with what we talked about is that this light ray was traveling in glass. Glass is going to have a higher n value than air. So when it hits the air, it's going to travel faster, and so it's going to bend away from the normal. The normal is not drawn on here. The normal goes perpendicular to that boundary. So that would be the normal right here. In this case, I would draw a normal right here. But in both these situations, you can see that as the light sped up, it meant it turned and went away from the normal. Eventually, there becomes a point, which we call a critical angle, where the light ray won't escape into the next material and it gets reflected back. So we looked at examples of where the light ray went from one medium to the next and refracted. We looked at ones where there was partial reflection, so you had a bit of both. There was some refraction as well as some reflection. And then you saw me a couple times run into the situation where I was trying to demo something, like with a diamond, and it didn't escape the medium at all. It was all reflected. So there's usually some sort of angle where you have that switch and that starts to happen. And so it is possible, as you can see here, that once you hit that angle, from there on in, as you continue to increase from there, you're just going to get pure reflection. Okay. Where this comes into an application is with fiber optics. So normally we would just talk briefly about that. You may have heard of fiber optics because it may be something that you've connected to or is coming through your neighborhood. And there are some advantages to this medium of communication using fiber optic cables, which is why some of you or your families might be excited about it. So just to explain how that works, I'm just going to borrow from this page. It's more of a talking point than anything. We have some information here. So when you have total internal reflection, this is what is happening. The light can't escape and it keeps getting bounced back. And each time it hits the glass, which is what a fiber optic cable is made out of, it gets reflected back, hits once again at an angle that causes full reflection, and just keeps bouncing like this. So you might not be able to see this very well, but it talks about how fiber optic cables are made of really, really thin pieces of glass. It says about the size of a human hair. And then they're cladded with something else, which means something else is put on top, a different type of glass that's a little bit more protective. And it says down here are the advantages. So instead of like a copper wire for transmission of your information, the benefits of changing to fiber optic cables is that signals are not affected by electrical storms because light and the transmission of light is not affected by electrical storms. They can carry and also tend to be underground. Most of the fiber optic cables get buried underground if they're in your neighborhood. They carry many more signals over longer distances, and they're smaller and lighter. Okay, so speed is a big piece. Obviously, light travels incredibly quickly. And so if you're transmitting things by light, it means that your connection is super speedy. Okay, so that was the last bit to it. If I just, maybe I'll just show you this little piece here as well. We labeled all these things in our own note. Move this here. But there's a different picture, okay, where you can see here's one material, here's the next. This would be pure reflection. Those angles are going to match. Angle of incidence, angle of reflection always match. Refraction means that the light can travel into the next material, but if the n value is different, it's going to either speed up or slow down. And so either come towards normal if it's slowing down, or away from the normal if it's speeding up. And there is a possibility to get both happening at the same time. So we have this here example of sunglasses. You're getting reflection, but you're also having the light transmit through as well to your eye. Okay. All right. The new and last piece for today is there's two more optical equations to talk about. And they're short and sweet compared to what you've seen earlier in the week. So I'm just moving over to my paper. We're going to start to take a note. So you can get your paper out like I have here. And then we're going to go to the last two optical equations, which can be blended together to make one. And that will be it for optical equations that you know. So we're going to put final optical equations as a heading for today. So we've talked about the thin lens equation, the 1 over f equals 1 over di plus 1 over do. We've talked about Snell's law, and then we have a couple here we can use for magnification. So you can not just predict where the focal length of a lens is or how far an image will be from the lens mathematically. You can calculate how much an image has been magnified by. So there's two magnification equations. A little subtitle there, magnification. The first equation, capital M, is going to stand for magnification in our equation, equals little h with a subscript little I divided by little h with a subscript little o. And maybe you've already figured out what these variables are going to stand for. So little h in equations is height. So both of these are heights. And little I and o indicate which height I'm talking about. For little I, this would be the height of the image. And little o means that we're talking about the height of the object. Okay, so I can figure out how much I've magnified something by if I have both the heights, or if I know the height of my object and I know the magnification of the lens I'm using, then I can calculate what the height of my image should be. So like everything we've looked at so far, you're usually only solving for one piece. If in this case there's three pieces here, if I know two of the pieces, I should be able to calculate for the third, whatever it is, no matter which variable the unknown is. And that's relying on your math skills. Okay, in this case, if I divide this by this and the number is greater than 1, okay, then that means I've got a larger image than I had object. Okay, so image is larger than object, okay, which should make sense to you. I magnified it by, if you're looking at a microscope, 40 times, 100 times, 400 times. I'm making it bigger than it was. If I get a number that is less than 1, then the image is smaller. Image is smaller. See, it's brighter today, so it's taking a while to accommodate that. Image is smaller than object. Okay, you don't need any units. As you know from the microscope, we're just saying how many times bigger it is. So no units required on this. Another way, so I can do or, to calculate magnification is with the distances. So I can do little d subscript I, little d subscript O, one divided by the other. We've already talked about that d stands for distance. That's another way to calculate it as well. Okay, we'll get you to the same thing. So if you like this stuff, if you like equations and problem solving and seeing how things together, if we had more time, we would introduce using another equation. So if you can find the same m using this or this, then it follows that this and this are the same as well. So there is a third equation, okay? I'm just going to write it over here, although we're not going to work with it much this year, is that hi over ho is equal to di over do. And if we have more time and we're going to pursue this further, we would talk about how you can, with these 4 variables, have 3 of them and calculate the 4th no matter what it is. So if I had the height of the object, the distance of the image, the distance of the object, I can calculate mathematically what the height of the image should be. If I know the 2 heights and I know the distance of the object, I should be able to predict where that image will show up, what its distance is from the lens. And so this can be used as well for solving any component to knowing the nature of the object or the image. Okay, so I'm going to assign some textbook questions to practice using this one and this one. And I think that's where I'm going to leave it. I don't even think I'm going to give you an example. Well, maybe I should. Let's make one up. Okay, so let's do practice. And I'm not going to write out a whole question. I'm just going to give you some information and then write down my givens. Okay, so let's start with the fact I want to know the magnification power of the lens I've been using. And I've done an experiment. The height of the object that I put under the lens was, let's say, 3.2 centimeters tall. And using my lens, I get an image that is, let's say, I don't know, 20.8, I don't know, centimeters tall. So I want to know the magnification of this lens. That is my unknown. I have all of these formulas here to choose from. I am going to select the one that has the heights in it. So I'm going with this one, height of image over height of object. And I get, 20.8. I can put the centimeters there. 3.2 centimeters there. You can see those cancel, so there's no units. And trusty calculator. 6.5. Oh, it came out so nice and round. And so this number is bigger than 1, so it makes sense that I'm saying that that is bigger than what I had to begin with. So the lens magnifies by 6.5 times the size of the original object. All right, so the textbook page for this is going to be 424, 425. I will attach an image so that you can see them and the answers. You can check them. And I think that's probably all there is to you need to know for now. Just trying to think. Sometimes if you see a negative sign, it just means it's upside down. It doesn't mean that it's a negative height. That doesn't even make sense. So if you run into a situation where you see that there's been a negative used in reference to height, it means that it's upside down. It's inverted. Okay. All right. That's it. Look at that. Shortest one yet. All right. I will check back with you for the next lesson, which will be all about mirrors. All right. Take care. Enjoy your weekend.